All right, so we're looking at exponential versus Poisson. And if you have the Poisson distribution, you're going to be interested in a discrete random variable. So in other words, your probability that you're looking for involves the probability that some number of logins, for example, is going to occur. So you're actually looking for the probability of sort of a digit, some kind of numerical value for example, the probability that a number of logins would actually occur. So I'm just drawing or writing out the Poisson distribution right here so you can see it, as opposed to the exponential distribution. This has a continuous random variable that you're looking for. So look, you're plugging in here, you're plugging in like a value for, we're looking for the probability that there are no logins within some set period of time that you plug into the equation. But here, the random variable that you're talking about is time, which is continuous. So we're going to write it. Here's our probability density function. It is lambda e to the minus lambda t for t greater than or equal to 0. And of course it's 0 if t is less than 0, and likewise this is 0 if t is less than 0. So look at carefully at what we've got going on here. It's as if we plug the time in here just to set a time frame that we're dealing with, but actually the primary number that we're interested in is this x, right? So it's the probability that this 5 logins will occur during whatever time scale we set. Here we're actually going to be interested in t as the random variable. So the best way to truly understand what's going on is to go to one of my very favorite problems ever in all of time, and that relates to this one, which is we're going to model user logins for a computer network as a Poisson process with a mean of 25 logins per hour. What is the probability there are no logins in a randomly selected 6-minute interval, 0.1 hours? Now, what I think is the reason I love this problem is because you can approach it in a number of different ways. It belies the usual humanist perception of engineers as being uncreative types that don't have lots of ways to solve problems. So that's part of why I love it. But let's look first, they say that this is a Poisson process. Now, because we are clever and we remember everything, we know that under the Poisson process that is characterizing this whole user login model we can apply it or understand it in 2 ways. We can characterize it directly as that Poisson process with a certain probability of x, where x is a number of logins, right? And so we can write this as lambda t to the x e to the minus lambda t all over x factorial, and that's where x is greater than or equal to 0. Otherwise it's going to be 0 if x is less than 0. Now, if this is the case and we're modeling it using this equation, we're asking what is the probability there are no logins in any randomly selected 6-minute period or interval. That's 0.1 hours. So we can say, well, let's see, we can plug in lambda. They tell us lambda is 25, and then times, it's 25 logins per hour, so we've got to have the hour there. So we're going to say 0.1, and we're raised to the x. We want 0. Oh, well, it actually didn't matter what I plugged in there because it's to the 0. And then we've got e to the minus 25 times 0.1 all over x factorial, which is, that's just 1 right there. So if you calculate this as all out, it's e to the minus 2.5, and that turns out to be 0.082. Okay, so simple, right? It is actually very simple. But let's do this with a different color. Okay, so now let's say that we want to use the idea that this particular situation can be modeled as a probability density function of this sort, e to the minus lambda t. And now the way we can look at this is we can say this probability density function is characterizing when the first logon will occur. So what we're saying for this particular problem is we want to know the probability that the first logon will occur somewhere between 0.1 hours and the rest of time. So if that's the case, then we can plug in it's 0.1 to the rest of time times 25 e to the minus 25 t dt, and when we do that integral, it ends up nicely canceling. That 25 is going to cancel by this 25 when it comes downstairs as we integrate. So it's minus 25t evaluated at infinity and 0.1, and that turns out to be minus 0.082, and then that finally is 0.082. By golly, it's the same as what we got up here before. Hey, yay us. Okay, so, but there's another way we can do this problem. So, let's move to green. Let's say that now what we're really interested in is the probability that some event occurred during the time frame from 0 to 0.1. In other words, if we have, we're going to use this same equation, but we're going to look at it in a different way. We'll say, well, first, before we do that, we'll say, what's the probability t an event occurs in 0 to 0.1 time frame. Well, you know that says time frame, even if it doesn't look like it. Okay, so we've got that. So we're going to just take and integrate from 0 to 0.1. And I know what you're saying is, but we don't want it to happen then. But don't worry, we'll handle that. E to the minus 25t. And that turns out to be, let's see, dt. E to the minus 25t evaluated from between 0.1, whoops, sorry, 0 and 0.1. So if we do that evaluation, it turns out to be 1 minus e to the minus 25, or 2.5, right? So if we have that value, that's actually quite different than this value. But what we had just calculated is the probability that an event occurs during this time frame. So it's like occurs in here. But we don't want that time. We want that it occurred after that time. So all we have to do is subtract this from 1. Right? So it's just 1 minus e to the minus 2.5. And that is e to the minus 2.5, which is 0.082. And voila! We have gotten the same answer in 3 different ways. Count them, 3. Okay, now we have an example of a difference again between the Poisson and exponential. Notice that we're going to be looking at the same Poisson process, but from 2 different perspectives. Give us 2 very different answers. So first, we can look at power surges at a power station, and they're thought to occur as a Poisson process at a rate of 4 per day. Okay, so the lambda is equal to 4 per day. But look at this. Okay, so, well, later they're going to try and cheat you, right? Because they're going to quantify in hours. So later we're going to have to deal with translating this lambda into hours. But to begin with, they say, what is the probability of 2 power surges in 1 day? Well, if we've got that, we can say the probability that x is equal to 2, equal to 2. Well, we just haul out our trusty Poisson process, and we're going to write it down here. So we've got it handy. It's going to be lambda t to the x all over x factorial e to the minus lambda t. And when you start plugging everything in, it's going to be, let's see, we want 2 power surges. So it's going to be lambda times t, which is going to be, what, 4 per day times 1 day, raised to the x is 2, and e to the minus, and you can see lambda t is just 4, right? So we're going to put that. And all over 2 factorial, which is 2 times 1, and that becomes e to the minus 4, well, basically 4 squared times e to the minus 4 all over 2, and when you work that out, it is 0.1465. So that's one way of working this problem. Now, but we could ask a very different question. We could ask, what is the probability that the time between 2 power surges is greater than 4 hours? Same phenomenon, but we're asking a very different question. What we're really looking for is, well, let's see. First off, we have to translate that lambda term into right now it's 4 per day, which is actually 4 in 24 hours, which is 1/6 per hour. Okay, so we've got that translated, and now we can say that the probability that t is greater than 4 hours is going to be, well, now bear with me. Now if we're thinking about this, we can say the probability that it's going to occur in less than 1 hour, probability that t is less than 4 hours, is going to be, well, we integrate from 0 to 4 lambda e to the minus lambda t dt. That's going to give us this. And if we subtract 1 minus this value, we're going to be in like Flynn, as they would say. So actually what we're going to have is, I'm going to take that, here's the first one, I just kind of took that over there, so here's that first one, and then it's going to be minus, let's see, we've got to integrate this little puppy. So I'm going to rewrite it as 0 to 4, and our lambda, remember, is going to be, our lambda is 1/6 e to the minus 1/6 times 4 dt. Okay, let's do the integration now. It's going to be 1 minus, now it's, let's see, 1/6 e to the minus 1/6. Oops, I should have kept that t there. Why didn't you correct me? I know you wanted to. Over 1/6. Oh, those two puppies cancel. Evaluated between 4 and 0. So that's going to be, well, let's see, the 0, when we plug that in there, that's going to be 1. So we're going to have 1 minus 1. Here's the first 1. The second one comes from integrating with the 0. So you can see those two things are going to cancel out. And then we're going to have minus minus, which is a plus, e to the minus 4/6. And that is the answer right there. We'll circle it. And so what we've got is the probability that t is greater than 4 hours. We know by now we can also say greater than or equal to 4 hours is just e to the minus 4/6, which is actually, if you want to calculate it out, 0.513. Okay, now let's go to get another look at this idea of a memoryless property. So let's suppose that the lifetime x in days of a certain component c is exponential with our beta. Remember, beta is equal to 1 over lambda, is 120. So I should point out that if this beta, well, the lambda is, we're used to failures per unit time, right? That would be lambda. And so beta is just something like time per failure. So it doesn't really matter which one is which one you use, because you can always convert things around. Anyway, if that component is still working after 100 days from the beginning of its tiny little life, find the probability it will last more than 340 days from the start of its life. So this is a trick problem, because you're supposed to remember that this is memoryless. In other words, it is as if at day 100 it is still brand new. So we're going to integrate from 0 to 240. So integrate from 0 to 240 days. And beta is equal to 120. So, well, lambda 1 over beta and that's 1 over 120. So all we have to do is just integrate here. We've got 0 to 240 lambda e to the minus lambda t dt, and that's going to become 1 minus e to the minus lambda t, and our limits are 240 and 0, and that's going to become 1 minus e to the minus 240 over 120, and all of that becomes 0.865, which is 0.135. Bingo. Check. We're now going to do problem 4-100, which I think provides a great illustration of the relationship between Poisson and exponential distributions, which are related at a very deep level. So first off, we have a number of stork sightings on a route in South Carolina, and they follow a Poisson process with a mean of 2.3 stork sightings per year. So they ask, what is the mean time between sightings? Now what I'm going to do is I'm going to bring over a copy of page 704. You see, whoops, where is 704? Here's 704. There's the page, and I can't write very easily on this, but it doesn't matter. Now look, here's the name of the distribution, probability distribution itself, the mean, and the variance. So let's go down for just a minute. We want to take a look at Poisson. Here's Poisson. There's the this is the funky way the book does it. Actually, I prefer if you write this Poisson equation, which your book uses this, I prefer you write it in this fashion because it'll keep you out of trouble. But one thing to notice is, look, Poisson has a mean, according to this particular book, of lambda. Now, what's interesting is to compare this with the exponential distribution. Here we see the mean is actually 1 over lambda. So what we have to do is go take a look. They're saying, what is the mean time between sightings? So which one do they mean for the mean? Well, if we look here, it says it's following a Poisson process with a mean of 2.3 per year. That means lambda is equal to 2.3 sightings per year. And indeed, when we plug that little lambda in here, what do we end up with? We end up with an exponential that has 2.3 sightings per year times some time, which we'll put it in year, right? These will cancel, and essentially we're left with a dimensionless. This is 2.3 per year of whatever we have. So am I using a bit of sleight of hand? Maybe, but the years cancel, and that's what we need. Now when we ask what is the mean time between sightings, that means time per sight or sighting. So we're going to have to take 1 over lambda to get that. And when we do that, 1 over 2.3, it becomes 0.435. Bingo. Okay, so now that's part A. For part B, what's the probability that there are no sightings within 3 months? Well, we can work that in 2 different ways. First, we can work it as the probability that x is equal to 0 is just going to be lambda t to the x. We're going to use this formula. for x factorial, and plugging in our numbers, we get 2.3, right? This is lambda's 2.3 times, well, it's 0.25 months, or I mean years, and we want no sightings, so this x is equal to 0, and that means it's 0 here too. 0 factorial, of course, is just 1, and then we can say e to the minus 2.3 times 0.25, and all of that becomes 0.5627. Alternatively, we can do things a different way. Alternatively, and that is, we can say, what's the probability there's no sightings within 3 months? Oh, well, that means that the sighting has to have occurred somewhere after that time. So we can look at it instead of probability of no occurrences, right, using Poisson. We can instead use the exponential and say, what's the probability it's going to occur somewhere in this, that the time during which the sighting will occur will be somewhere between 0.25 years and infinity years. And we integrate our exponential distribution, and we find that it is minus e to the minus lambda t, right? When you integrate, that lambda comes downstairs, and right, so I'll do it properly here. Right, so the minus lambda came downstairs. I put the minus sign here. This comes upstairs. So we're integrating from 0 to infinity of minus e to the minus lambda t. And that becomes, oops, not 0. Why didn't you correct me? 0.25. That becomes minus e to the minus 2.3 t evaluated at infinity and 0.25, and that becomes, well, look at this. See how this part up here became 1 divided by 1, and we were left with e to the minus 2.3 times 0.25? Well, look at, all we're left with right here is e to the minus 2.3 times 2.5. So it devolves to the same thing, and all of that, of course, becomes 0.5627. So this is, we can say this is solution Dagger, and this is solution double Dagger. And if we wanted to be fancy, we could have solution triple Dagger, and that would simply be 1 minus the integral of from 0 to 0.25, right? That the whoops, I forgot the minus sign up there. Minus lambda t dt, and this is the probability that the sighting would occur somewhere in those first 3 months. So we want actually 1 minus that, and if we work it all out, it turns out to be the same, 0.5627. Now what about C? What's the probability that the time until the first sighting exceeds 6 months? Well, we can do it pretty much the same as we did the previous one. So we'll say, well, first off, we could say that that first sighting occurs lambda t to the x, e to the minus lambda t. Just use our same equation again, and now we're going to plug in numbers, and that is, or those numbers are, well, lambda is going to be 2.3 again, and then now it's 6 months. So we want that first sighting, or actually that within that 6 month period, which is 0.5 years, we have 0 sightings. So it's 0 here, e to the minus 2.3 times 0.5. And that becomes 0.317. So this was solution technique Dagger, and now we'll have solution technique double Dagger, which is simply, we can say, well, okay, before we were looking for the probability that there's no sightings during the first 6-month period. So another way we can look at this is to say that the sighting actually occurs somewhere after the 6-month period, all the way up until infinity. So it's lambda e to the minus lambda t dt, and we do the integral, and we end up with e to the minus lambda t, integrating from infinity to 0.5 to infinity, and this becomes e to the minus 2.3 times times t, and integrating from 0.5 to infinity is equal to e to the minus 2.3 times 0.5. Oh, wait a minute, look at that. Isn't that exactly what we had last time? Right? So it turns out to be the same thing, and indeed we get the same answer, which is 0.317. Triple Dagger, we can say, okay, it's going to be 1 minus 0 to 0.5 lambda e to the minus lambda t dt, and that becomes, well, 0.317. So 3 ways to work it, all the same answer. Lastly, what's the probability of no sightings within 3 years? Well, you're starting to see the pattern here. No sightings, well, first we could work it with Poisson. Poisson, we can say the probability that we'll have no sightings. We use the same expression again, x factorial, plugging in our numbers, 3 years, count them 3. So now we can say 2.3 times, the period is 3 years. I'm doing everything in years. I'll put that, and then 0, and 0 factorial, because we want no sightings during those 3 years. E to the minus 2.3 times 3, and all that becomes 0.001. Now, alternatively, this is our Dagger expression. Double Dagger is going to be, well, we can go from 3 to infinity of e to the minus lambda t, dt, and that becomes minus e to the minus lambda t, infinity, and 3, and then that becomes minus e to the minus 2.3 times 3, whoops, we've lost our minus, oops, and that becomes plus, right, which is 0.001. So that's double dagger. Triple dagger, as you might expect, is 1 minus 0 to 3 lambda e to the minus lambda t dt. Oh, I might have forgotten that lambda earlier, so sorry about that. And that just becomes 0.001 when you plug in the numbers. So each one, or of these latter 3 anyway, has 3 different ways to solve, but they all lead to the same answer.